Hi everyone, I'm Bruno from MOVEdot. Welcome to the fourth episode of our tutorial series where we're developing a sports car together using VI-CarRealTime. So far, our work was focused on improving the performance and handling characteristics of the baseline sports car, and we had great results. Now it is time that we evaluate its ride characteristics. For that, we're going to run a series of maneuvers allowing us to quantify comfort and vertical load consistency on the tire contact patch. We'll then analyze the compromise between these different characteristics and further develop our dampers. We'll start the process installing extra sensors on the vehicle, allowing us to quantify these characteristics. Then we're going to learn how to create custom road profiles. And finally, we're going to run maneuvers to quantify ride and comfort behavior.
As usual, let's head to the File menu and load the trackcartutorialsession.xml file. Let's also create a backup of our model from the previous episode when we worked on aerodynamics by cloning it to the same database we've been using and naming the clone trackcar_EP03. Save the new clone and delete it from the tree view.
Comfort is subjective. And to analyze it, we'll be observing vibration and harshness using metrics provided by the ISO norm 26311. With those metrics, we can understand how vertical inputs on the tire contact patch will be transmitted to the chassis and in the end to the driver as the car drives over rough surfaces and bumps. One of the metrics that we will use quantifies ride harshness as an acceleration value. We have reference values provided by the norm that allow us to quantify the comfort level. As we can see, we have ranges that go from not uncomfortable to extremely uncomfortable. We're also interested in peak vertical acceleration, for example, as the car drives over a bump, as well as the total amount of vertical load acceleration that the driver is exposed to. Now, let's focus on installing the sensors that we need on the car in order to be observing and quantifying these characteristics.
We have to install an accelerometer to the seat rail. This gives us a consistent reading of acceleration based on the chassis and suspension properties, ignoring the influence of the seat itself on comfort for now. In build mode, select the track car's body subsystem and click the User Sensor tab. This is where we can create new virtual sensors to monitor data we don't have available in the output channels by default, like our very specific seat rail sensor. We will start by naming our new sensor front seat rail. For this sensor's type, select Acceleration and click Add. It now shows in the user sensor list, and we can set up its properties by double-clicking it. Set the type of freedom to translational, as we're interested in monitoring linear accelerations. Set the I marker to front chassis, meaning what the sensor is attached to, and the J marker to the ground, representing with relation to what the sensor will be measuring the body accelerations. We also have to select a reference for the sensor for which we're selecting gyro. Let's position the sensor at the center of the driver's seat rail. According to the car's reference system, coordinate x equals to minus 1,300 millimeters, y equals to 400 millimeters, and at z, 240 millimeters. The sensor is now properly set up, and it will monitor accelerations in all three dimensions, at the seat rail with relation to the ground. If we want, we can come here to change what the output channel for each component of the measured acceleration will be called. The suggested names follow what we called the sensor itself, and we will keep them like that. We still have to activate the new sensor. To do it, click the track car's root folder, head to Output Channels tab. Click Update Map so that the model can identify the new sensor. Click the Save icon to register this update. Select the track car's database and name it Track Car Output Map. Confirm and save all of the model to the database. To double-check if the new sensor is active, expand the output channels tree and look for the front seat rail acceleration components. To analyze comfort, we will simulate track tests that could be performed with a real car. In one of the tests, the car will ride at a constant speed over a controlled rough surface, while the other one will analyze how the car rides over a speed bump. We can create roads perfectly matching our requirements using VI Road that we can find by opening the Utilities menu and clicking it. VI Road is a module that allows us to design and customize the roads, surfaces, and paths we use in VI-CarRealTime. Let's load something into it so that we can study its main features. In this main screen, click here to browse for VI sample road analytic.rdf file and select it. Then click here to browse for VI sample road analytic.drv.drd, and here to open them into VI Road. Notice a track layout was loaded in the 3D viewer. We can move the camera around like we did in the animator by left-clicking to rotate, middle-clicking to pan and scrolling, or right-clicking to zoom. On the top of the screen, we can find a toolbar including these same camera commands, the option between orthographic and perspective projections, the ruler icon that will display the technical characteristics of whatever point of the track we hover over, and this option to display the mesh for the road model we have on screen. The menu to the left displays the properties for the tool that is currently selected. The default are the load options we used before, but if we click around the toolbar, we can see the options change. At the very bottom, we can change the left menu into the tree view that displays the elements that are currently loaded on the scene. Now that we understand VI Road's user interface, let's take a brief look at some of the ways we can use it to create and edit roads. Depending on how you intend on creating a new road and what kind of input data will be used, a different method may suit the process better. This tool right here, for example, is meant for the creation of symmetric oval tracks from scratch. And we can use the Analytic Road tool to design road tracks. Within it, this first box allows for the creation of the track layout. We can design a road center line by adding its length coordinate to the cell on the left, and the road's curvature at that control point to the cell on the right, which can be defined either as curvature or by the local radius at that point. We can also choose between setting the distance either from the road's starting point or as incremental from the previous control point. By adding some values here and clicking Create on the very bottom, the road will show up in the 3D viewer. If we check Interactive, the next changes we make will load into the model instantly, like for example, if we add some height to a certain point of the track, it shows up immediately. And the same will happen if we adjust the road's banking or width. And finally, the output step controls the road's resolution, as in how long each segment that composes the road will be. We can highlight them here and change the value around to see its effect. If, instead of creating a road from scratch, we would rather recreate one we have data for as, for example, a .knl or a .knz path file exported from a mapping software, or even a .csv coordinate sheet generated from telemetry, we can do it here. It's the same tool we used when we loaded the example track files, and the process is the same for any of the supported formats. Let's load those same example ones again. To observe small details on large roads like this one, we can use this tool to set the 3D view pivot point to wherever we want, by clicking the place we wish to observe and zooming into it. This icon resets the view to fit everything on screen. We can also edit the base roads we create and add features to them. Similarly to how we could define the general characteristics of the analytic road, we can also include and edit other details like curbs, roughness, and surface friction to it. These tools right here are meant for whole track transformations, good for reorienting and smoothing out paths and center lines, for example, while these are dedicated to path design and manipulation, something we won't do in this video. The last editing tool we will talk about today is the Extrusion Road tool, where we can split our road into sections and design the profile of the road for each of them. VI-Road includes its own help file, accessible here, where we can find more details about all of the methods and tools we've seen and more. VI-Grade also offers a wide selection of roads officially modeled after racetracks and test facilities from all over the world, ready to be used for online and offline applications, with different pricing plans suited for your needs. You can visit VI-Grade.com for more information about how to get access to them. And if you don't find the track you're looking for, send a message asking about the feasibility to add it to the list. Let's now focus on creating the roads we will need for our ride tests. Our test scenarios are very simple to make, so follow along as we create them together. By driving over a speed bump, we can investigate the accelerations transferred to the seat by the initial impact, as well as what happens afterwards as the car oscillates back to equilibrium. All we need for a test like this is a smooth, straight road with a speed bump in the beginning so that the car has plenty of room to travel after overcoming it. To start, click here to create a new road model and confirm. Go to Analytic Mode and name our new road as Speed Bump 1590, where the numbers refer to its main dimensions, in millimeters. On the very bottom, enable Interactive Design Mode, so that we can observe the new road unfold as we model it. On the Plant Definition box on the top of the Property menu, set the road's starting point at 0 meters with a curvature of 0, and the ending point at 300 meters, also with a curvature of 0. At the very bottom, change the output step to 0.037 meters, as we will need it to be small so that it suits the resolution at which we will trace the speed bump's profile using the height definition box. Click the cell on the second row where it says 300, type 50, and hit Tab on your keyboard to move to the next cell. Notice that this created a new row in between 0 and 300. Type 0 for this point's height value and hit Tab again to go to the next row. Type 50.15 for length, hit Tab, type 0.025 for this point's height, and hit Tab again. Keep doing this process until you add the remaining values in the sheet that is on the screen right now. While doing so, notice how the speed bump takes shape at the beginning of the road. Select the Pivot Point tool and click that area to center the view around it, and zoom in to look at it a little closer. When the profile is finished, select the Export tool, keep the default options, and click the button on the bottom. On the Save prompt, navigate to where our working directory is located and create a new folder for our roads. Save our speed bump road within it, and it is ready to be used in VI-CarRealTime. The rough road testing is intended for observing vibrations from continuous stimulations. The road itself is very simple to make. Once again, select New to start another design, open Analytic Mode, and name the new road Straight Rough 3 kilometers. On Plant Definition, start the road at 0 meters with 0 curvature, and finish it at 3,000 meters, still with 0 curvature. Increase the output step back to 5 meters, and, in case interactive mode is not selected anymore, click Create. So far, this is a smooth 3 kilometers straight road. To add roughness, open the Irregularities tool, click Create, and check this box to activate the default roughness. Doing this allows for the setting of the roughness in terms of PSD irregularity definition. That itself defines the power for each frequency present on the road profile. We will keep them unchanged for this one. Click Set on the bottom to apply the choice, and export the road like we did for the previous one, at the same location. We can now close VI Road and go back to VI-CarRealTime. Both the car and our roads are ready for our comfort studies. We will investigate how the car behaves as it runs through each of them multiple times, in a wide range of damper settings. Pachejka tire models won't allow us to perform accurate ride analysis due to the high-frequency nature of these maneuvers. We recommend using advanced tire models that cover a wide range of frequencies, and most are natively supported by VI-CarRealTime. As we learned in the previous episode, to create an investigation, we first need to define the tests we will be investigating. In test mode, hover over the event bookshelf and look for the Straight Maintain event. Right-click it and add it to a new fingerprint. Select the new event in the tree view to bring its settings to the property editor, and let's set them up like this. End time at 8 seconds, initial velocity at 15 km per hour, gear as 1, initial throttle as 20%, parameter to be maintained as velocity, straight line set to yes, and check the straight setup box. For the solver settings, adjust the output time step to be 0.002. And on the road data file field, browse for the speed bump 1500 90.rdf file we created. Go on Vehicle Settings to activate Update Vehicle Location and click Automatic Z Location. Also, change the X Vehicle Location to 36,000. Name this event Track Car MNT Speed Bump. And for the second event, select the same fingerprint, and from the bookshelf, add another Straight Maintain event to it. Select the new event and configure it by setting end time to 100 seconds, initial velocity to 80 km per hour, gear to 4, initial throttle to 20%, select the velocity as the parameter to be maintained. Also define this test as a straight line and check straight setup. Adjust this event's output time step to be 0.002, like in the previous one. And finally, browse for the rough road data file we created. Call this event Track Car MNT Rough Road. Now, select the fingerprint containing both new events and click Play to run the simulations. Once the test simulations are done, we can proceed to the investigation mode. Find the speed bump event in the bookshelf and right-click it to add it to a new investigation. Select it in the tree view. In the candidates list, look for the front damper's scale factor. Right-click it and promote it to a factor. Do the same for the rear damper scale factor. We're going to define both factors the same way, so you can follow along for the first one and then apply the same settings to the second, using the checklist on screen. On the factors list, right-click the first one and add it to a new group, which will be group 1. Select its type to be continuous and delta type to be absolute. Set the lower limit to 0.1, the upper limit to 4.1, and split it into 17 levels. Change the simulation mode to Inherited from Event and make sure to select Full Factorial Type. Now, do the same for the other scale factor of the damper. We can now define the responses we will monitor in this investigation. Click to Add a Response and select it on the list. Name it Impact, as it will monitor the highest acceleration felt by the driver when hitting the speed bump. Change its function to Maximum Value and check Use Absolute Value, and browse for the Front Seat Rail Sensor.ac CZ output channel, which is the vertical component of the sensor we added to the seat rail. We can then add a second response and select it. Name this one Seat Acceleration Area, as it will measure the integral of the vertical accelerations measured at the seat after going over the speed bump. Change its function to Custom Computed Value. Browse for the following two output channels in this order: Time, all caps, and Front Seat Rail Sensor in the Z-axis again. It's important that we select the output channels in the correct order, because this is what dictates how they will be read in post-processing. And speaking about post-processing, We will be looking at custom metrics for some of the investigations in this episode, so download the scripts for them from the description of the video, unpack, and move them to the scripts folder we created some episodes ago, which should be located besides your working directory. Now, back in the investigation settings, in the custom Python script field, browse for the seat.a.cc area.py file among the new ones you just downloaded, and name the output folder Investigation Speed Bump. With this, the speed bump investigation is ready to run. But let's prepare the other one before we move forward with it. Find the rough road event on the bookshelf and add it to a new investigation. This investigation is going to be very similar to the other one. So instead of setting everything up from scratch, we can borrow settings to use as a starting point. To do so, right-click the new investigation in the tree view, select Import Settings from, and pick the previous investigation from the prompt. This is good because we will use the same factors for this investigation, so we don't need to set them up again. Just make sure to select Full Factorial Type and set Simulation Mode to Inherited from Event. We do need to define the responses for this new investigation though, so remove the existing ones. Now click to add a new response and select it. Name it ZEET RMS, set the function to custom computed value, browse for the output channels again, and select time, and front seat rail sensor.accz in this order once again. And for the custom Python script, browse for the ACC RMS seat.py file. Name the output folder Investigation Rough Road. Everything is ready for us to run the simulations now. Since we will be running 2 investigations at once, it may take some time to finish, so save the investigation setup and save the session before we do so. On the tree view, Control-select both of the investigations we created and click the play button to start them. Confirm the prompts to initialize the first investigation and stand by to confirm the prompts for the second one. When the investigations are done, select the speed bump one on the tree view and open its design space and results. We can have a good idea of what is going on here by scrolling down to analyze the results plot. If we focus on the impact column, we can directly read the magnitude of the acceleration the driver will feel when first hitting this kind of obstacle. We can also observe that, as expected, the magnitude of this acceleration rises with the damper stiffness, but there are outliers. The peak acceleration rises at this one instance in the bottom, despite the damper stiffness being the lowest in the whole test. This happens because the damping is so low at this point that the suspension hits its bumper at a high speed, causing another impact, even harsher. On the other end of the plot, we can observe a region where our damping adjustments don't have very significant impact on the acceleration anymore, suggesting this setting is saturated and any further stiffening would be practically meaningless, at least for dealing with this kind of obstacle. In terms of shock absorption, the milder the impact being transferred to the driver, the best the ride should feel. Therefore, the ideal solution for a comfortable ride in terms of dealing with severe bumps and obstacles is the softest damping setting, as long as the suspension doesn't bottom out. The seat, a CC area column, can be read as an index for how much vertical acceleration in total is felt by the driver as the car stabilizes after hitting the bump. Therefore, the lowest the value, the less the driver will be disturbed and the more comfortable the ride will be. Any damping scaling factor in between 1 and 3 seem to deliver good results here, with the very best alternatives being the ones closer to 2. Let's analyze what happened at the rough road investigation by selecting it and opening its design space and results. Scroll down to focus on the plots. We can observe a similar effect to what happened in the impact analysis, where the lowest setting is also increasing the measured acceleration. And this also happens here for the same reason it did there. Also, the values on the seat RMS column can be directly compared to the reference table from the norm. We don't have a solution that guarantees the car is very comfortable according to the table, but we can at least try and aim at avoiding getting into the very uncomfortable range by not going over around 2 times the standard damper stiffness. To sum up our analysis, we found out that to make this car as comfortable as possible, while only tuning the dampers, we need to keep it as soft as we can, as long as we have enough damping to dampen the oscillations, and the suspension doesn't bottom out, meaning our lowest scale factor acceptable is 1.05. Damping factors in between 1 and 3 seem to be at a good range for oscillation control, and we should avoid going over scale factors of around 2. And with this, we now know that to make sure our track car is not uncomfortable to drive, we should aim at damping levels in between 1.05 and 2 times the ones from the original dampers. The slow damping ratios of our original dampers are around 0.54, over which we already have applied a scaling factor of 2.2 for the front dampers and 2.8 for the rears. However, the dampers of a sports car should not only provide an acceptable comfort level, it should also provide good control of the body. So, in our next episode, we will keep expanding our ride analysis. With these results in hand, we can save our session as we finished all we have set to do in this episode. Today, we performed ride studies focused on understanding how to optimize our track car's dampers for comfort. To do this, we learned how to add custom sensors to our model. We explained how to create our own road files using VI-Road, and we also ran investigations using custom processing scripts. With the analysis performed, we were able to find optimal damping levels for comfort behavior, while providing a stable platform. In our next episode, we will use post-rig testing to optimize tire performance, quantifying and minimizing vertical load variation. I will talk to you soon.